Okay, so let's talk about equilibrium now, and this will be for worksheet 9.2. So, equilibrium concepts. All chemical reactions are reversible. They do not proceed only in one direction. So, chemical reactions occur at in both directions at the same time, almost from the very beginning. Now, one reaction will be happening much faster than the other at any given time until you reach equilibrium, and then they will be occurring at the same rate. So, this is a very dynamic process. They are constantly occurring all around us. In fact, most of the processes within your body necessitate that these reactions are reversible. We can take sugar from our blood, convert it into fat, but then we can also take that fat and convert it back into sugar so that we can have an energy source. And that's just one of thousands of examples. So, a chemical reaction is usually written in one way. Typically, the forward reaction is the one we want to have occur, not necessarily the one that will occur most quickly. And since they are all reversible, we typically use a double-headed arrow. And again, during this presentation, you should start, stop, write down as much of this information as you need. I'm just giving you the high points. So while they're all reversible, some proceed more quickly or more entirely towards the products or reactants under certain conditions. But equilibrium is when the forward and reverse reaction are both occurring at the same rate, or there's no discernible change. And one word you should probably get familiar with for this topic is dynamic. It's a dynamic process. Oh, and there it is. Equilibrium is a dynamic process. Both reactions are still occurring even though I can't see or detect any change in concentrations. That means that I'm at equilibrium. When I'm at equilibrium, delta G would equal 0 and KEQ would equal Q. And we're going to talk about those two in just a minute. So it's not that the change stops occurring, it's that they're both still occurring just at the same rate, and we cannot detect a difference. So in general, if we have A plus B gives us C plus D, and they've got those coefficients, in kinetics, we cannot use the equation to write the expression, but in equilibrium, we can. So we would raise C to the C power and D to the D power divided by concentration of A raised to the A power and concentration of B raised to the B power would equal Q. And that's the equilibrium constant for this, or reaction quotient for this reaction, and that's QC. What else do we know? Well, the numeric value for QC depends on the concentration of the products and reactants, and when Q is determined in terms of what's happening in the reaction. Did I just add reactants, or has it been going for a while? Those will all affect Q. So when it reaches equilibrium, we no longer see a change, and the reaction quotient will no longer change. So when a mixture of reactant products reaches equilibrium, and again, this is temperature dependent, its equilibrium quotient, or QC, reaction quotient, has the same value. And this is true. This value is also called the equilibrium constant, and I often write this as K with a subscript EQ, and you should write that down. They just have K here, but I use KEQ. And so if it's homogeneous, that means all the reactants and products are in the same single phase, whether that's in the gas phase, if that's in an aqueous phase, there's no mixture of different states of matter, then it's a homogeneous equilibrium. If one of the reactants and or products is in a second phase, whether that's a gas with a liquid or aqueous with a gas or an aqueous with a liquid, something that maybe isn't miscible, like if you had oil and water and a reaction has to take place between those two phases, that would be an example of a heterogeneous equilibrium. So, what can happen about K, Q, and K. So the equilibrium position, if we have a set of reactants and product concentrations, we can fill them all in K in that Q expression, and then we can compare it to what K is, and we have to be given one and calculate the other. And so if Q for a reaction quotient at any particular time is greater than K, then the system will shift to the left to achieve equilibrium, and to the left would be reactants. If Q is less than K, the system will shift to the right, which is products, to achieve equilibrium. And if K equals Q, then it is at equilibrium. And so you can be given calculation. You can be asked to calculate the reaction quotient for any time with any certain values, or you can be told a system is at equilibrium and these are the concentrations of the reactants and products. Calculate K. So a small k means equilibrium lies to the left, and a large K indicates the equilibrium lies to the right. So K has no effect on the speed of the equilibrium. It just tells you which direction the equilibrium lies to, products or reactants. And so we're going to start with Le Chatelier's principle on the next video. Thank you.